right? Yeah. Elementary number theory and methods of proof. More direct proof and counterexample, but this is writing advice. How to write a proof, starting with universal statements. The following rules of style have become fairly standard for writing final versions of proofs. First, copy the statement of the theorem to be proved on your paper. This kind of goes without saying, keep your eye on the ball, eye on the prize. What are you trying to prove? And make it clear to whoever's reading it what you're trying to prove. Clearly mark the beginning of your proof with the word proof. The stating the theorem here, you might have some discussion as to why you think it might be true, or what have you. Expound on the theorem and why it needs to be proven, or whatever. The next section should be clearly marked. Okay, that was discussion, that was theory, that's whatever. This is the proof. Clearly stating clearly delineating the sections is important. Make the proof self-contained. That means if you're going to be declaring a variable, or if you're going to be using a variable, you should declare it. It's kind of like in a computer program, at least in C++ and most other languages, you have to declare your variables before you use them. You need to declare what they are, what the variable is, and what they are. What can they contain? Like suppose m and n are any even integers. You're declaring the symbol and the data type, to use programming parlance. You can give restrictions on it when you declare it. Let x be a real number such that x is greater than 2. That sort of thing. At a later point in your proof, you may introduce a new variable to represent a quantity that is known at that point to exist. That's okay. If you have an integer n and it's even, you know that n equals 2 times some integer, you can give this integer a name so you can work with it concretely later in the proof. So n equals 2s, for some integer s, you can use s later on. And you know that it is an integer. So you're declaring it by using it and stating what can be contained in s. Write your proof in complete, grammatically correct sentences. That doesn't mean don't use symbols or equations or abbreviations. You should just include them in sentences. For theorem 411, this contains the sentence, then m plus n equals 2r plus 2s. That is a grammatically correct statement. It uses symbols and variables and that sort of thing, but it is a complete sentence when read out loud. In a sentence, you can also include the second line of it to mean which equals this by factoring out 2 and by substitution up here. So use complete sentences and tie them together. Keep your reader informed about the status of each statement in your proof. Readers should never be in doubt as to whether something in your proof has been assumed or established or is still to be deduced. If something is assumed, preface it with assume or suppose. If it's still to be shown, preface it with we must show that, or in other words, we must show that. This is especially important if you introduce a variable in rephrasing what you need to show. Give a reason for each assertion in your proof. Each assertion in a proof should come directly from the hypothesis of the theorem, or follow from the definition of one of the terms in the theorem, or be a result obtained earlier in the proof, or be a mathematical result that has previously been established or is agreed to be assumed. Indicate the reason for each step of your proof by using phrases such as by hypothesis, by definition of, or by theorem such, and so forth. But each step needs to have a reason for it. Include the little words and phrases that make the logic of your arguments clear. Indicate how each sentence is related to the previous one. Does it follow from the previous sentence or from a combination of the previous sentence and the earlier ones? Begin the sentence with the word because or since and state the reason why it follows. Include the reason why it follows at the end of the sentence. If a sentence expresses a new thought that does not follow from an immediate consequence of the preceding statement, but it's going to be needed later, introduce it by writing observe that, or note that, or recall that. Sometimes in a proof it is desirable to define a new variable in terms of previous variables. In such a case, introduce the variable with the word let. Actually, in an old version of a old programming language, that's how you declared a variable. Let x equal such and such. That was the syntax of the language. They don't pretty much leave that alone now, but yeah, define a new variable in terms of a previous variable. Like suppose x is an even number, therefore x is equal to 2k for some integer k. That's introducing a let k equal be an integer such that n equals 2k, as an example. Display equations and equalities. The convention is to display equations and inequalities on separate lines to increase readability. Also makes it easier to check your work. Easier to follow, easier to check your work, that sort of thing. Okay, variations among proofs. Well, proofs are like writing papers. Even if the topic is the same, the subject is the same, the conclusions are the same, no two people write the same paper. Not word for word. Same with proofs. Programming. People have their own programming style. If you know what to look for, you can tell how many people have worked on a program by how many different styles there are in the programming. Because everybody's different. Everybody develops their own style and uses their own thing. So everybody's different, and you doesn't mean the proof is less valid because it's not identical to somebody else's. Common mistakes. The following are some of the most common mistakes people make when writing mathematical proofs. Arguing from examples. Just because something is true with a few examples doesn't mean it's true in general. Uses the example of the proof that the sum of any two even integers is even. This is true because if m is 14 and n is 6, which are both even, then m plus n equals 20, which is also even. That's just one example. It doesn't mean it's true for everything. So don't use. You can use examples to get an idea of whether or not you think a statement is true or a theorem is true, but you can't use it as a form of argument in a proof. Must give an argument to show that the conclusion is true for any arbitrarily chosen elements in the domain, not just for one or two examples. Using the same letter to mean two different things. Think about a symbol or letter that you're using for a variable. It has scope. They're in computer science terms, they have global scope. So you declare a variable at one point in the proof. Its scope is the entire until the entire proof is over, and through the end of the proof. It gives an example. If m equals m and n are any two odd integers, then by definition of odd, m equals 2k plus 1, and n equals 2k plus 1, where k is an integer. Well, if that were the case, m would equal n, right? So that only shows that m equals n, and that m and n are both identical integers, odd integers. So the proof only shows that the sum of two identical odd integers is even, not that the sum of two arbitrarily chosen odd integers is even. Third mistake, jumping to a conclusion. You allege the truth of something without giving an adequate reason. Consider the following. Suppose m and n are even integers. By definition of even, m equals 2r and n equals 2s for some integers s. Then m plus n equals 2r plus 2s, so m and n is even. Sounds like you're missing a few steps there, or one or two steps. This proof jumps to the conclusion without having found an integer that would be that when doubled equals m plus n. The fourth mistake, assuming what is to be proved. To assume what is to be proved is a variation of jumping to a conclusion. Consider this. Suppose m and n are any odd integers. When any odd integers are multiplied, their product is odd. Hence, m and n is odd. It's just assuming what you're trying to prove is true, rather than proving it. So, confusion between what is known and what is still to be shown. It's a more subtle way of jumping to a conclusion. It happens when the conclusion is restated using a variable. Here's an example of a proof that the product of two odd integers is odd. Suppose that m and n are any odd integers. We must show that m and n is odd. This means that there exists an integer s such that m times n equals 2s plus 1. Also, by definition of odd, there exists an integer a and b such that m equals 2a plus 1 and n plus equals 2b plus 1. Then m equals 2a plus 1 times the quantity 2b plus 1, which equals 2s plus 1. So since s is an integer, m and n is odd by definition of odd. Sounds like you're missing a few steps in there. But it just restated the conclusion to be shown, not how it should be, how it got there. Author just jumped to an unjustified conclusion. It could have been avoided if the author had written, this means we must show that there exists an integer that s such that mn equals 2s plus 1. Better way to avoid this kind of error is to not introduce a variable into a proof unless it is either part of the hypothesis or deducible from it. Another common mistake, number 6, is use of any when the correct word is some. Now, there are situations where they can be used interchangeably, but some for some integer a means that there is one integer a you're looking for. For any integer a means it doesn't matter what a is. The statement you're trying to say is supposedly true. The square of any integer is odd, which uses any as when the correct word is some here. Suppose m is a particular arbitrarily chosen odd integer. By definition of odd, m equals 2a plus 1 for any integer a. No, that wouldn't work because it's for some particular a. Just one value of a works for m. That value being m minus 1 divided by 2. The misuse of the word if. Not serious in itself, but it reflects imprecise thinking and sometimes leads to problems later in a proof. Suppose p is a prime number. If p is prime, then p cannot be written as a product of two smaller positive integers. Well, you're stating that p is a prime number, then you're questioning whether it is a prime number. Imprecise thinking. It doesn't really work out very well. it suggests the primeness of P is in doubt, but P is known to be prime by the first sentence. Cannot be written as a product of two smaller positive integers because it is prime. So the correct version of the fragment would be, suppose P is a prime number. Because P is prime, P cannot be written as a product of two smaller positive integers. All right, let's see here. Prove that the difference of any odd integer and any even integer is odd. Use only definitions of odd and even and the assumptions listed below, not any other properties of odd and even integers. We went through these assumptions on Tuesday. These are the basic laws of algebra, properties of equality, the principle of substitution, and the addition, subtraction, and multiplication being closed for all integers. Follow the directions given in this section for writing proofs of universal statements. Develop a careful proof. Rewrite the statement. For all integers a and b, if a is odd and b is even, then a minus b is odd. Is the way to refer to it. One way. Thus, the starting point for your proof should be something like, suppose a is any odd integer and b is any even integer. The conclusion should be to show, the conclusion to be shown would be, we must show that a minus b is odd. If, in addition, you know how to use the definitions of odd and even, you will have reduced the creative part of the developing the proof to a small but crucial section in the middle. So they don't go into the full proof of it, but it is provable, and it leads to theorem 4.2.1. The difference of any odd integer and any even integer is odd. Find the mistake in the following proof. If n is any even integer, then negative 1 to the nth power equals 1. Suppose n is any even integer. By definition of even, n equals 2a for some integer a. Then minus 1 to the n equals minus 1 to the 2a by substitution. And then that equals minus 1 to the a to the squared. And then that would equal to 1 because any non-zero real number squared is positive. Where's the mistake? Jumping to a conclusion on 5, it's not assumed to be true. Although it is true for the square of any non-zero real number is positive, it does not follow that the square of negative 1 to the a is 1. Exercise 10 at the end of the section asks you to give a correct proof of this theorem. And showing that an existential statement is false. Well, to show a statement is false, you prove that the universal statement that is its negation is true. So, show that the following statement is false. There is a positive integer n such that n squared plus 3n plus 2 is prime. Well, you got to proving it false is equivalent to proving its negation is true. Its negation is, for all positive integers n squared plus 3n plus 2 is not prime. Because the negation is universal, it is proved by generalizing from the generic particular. There is a positive integer n such that n squared plus 3n plus 2 is prime, is false. So, gotta prove that. Suppose that n is any positive integer. Factoring that shows that n squared plus 3n plus 2 equals n plus 1 times n plus 2. In addition, n1 and n2 are integers because they are sums of integers. And both n plus 1 is greater than 1 and n plus 2 is greater than 1 because n is greater than or equal to 1. Thus, n squared plus 3n plus 2 is a product of two integers each greater than 1. So, the equation does not yield a prime number. And that's it for this section. The next section is fairly brief. I'll go to the beginning. All right, so direct proof and counterexample 3, section 3, rational numbers. A real number is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. A real number that is not rational is irrational. Formally, R is a real number, then R is rational if and only if there exist integers a and b such that R equals a over b and b does not equal to 0. So, is 10 over 3 a rational number? Huh? Yeah, it's a ratio of two integers. So same with 5 over 39, 2.281. It's 281 over 1,000. So it's a rational number as well. 7? 7 over 1. 0? It's 0 over 1. It's two integers. 2 over 0? No, because the denominator has to be non-zero. A non-zero integer for it to be rational. Is 2 over 0 an irrational number? No, it's not a real number, so it can't be irrational. An irrational number has to be a real number, not a number. And actually, if in some programming languages, if you do a divide by 0, it won't throw an arrow. It will return NaN, not a number. Some programming languages will return infinity as the number infinity. But because the limit of 2 over x as x approaches 0, the limit would be infinity. So let's see here. Is 0.12121212 yada 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 are assumed to be Or is that a rational number? What it is, I don't remember. I don't remember from the previous class, but yes, it is a rational number, and it can be shown that any repeating decimal, even though it goes on infinitely, can be a rational number, or is a rational number. If m plus or m and n are integers and neither m nor n is 0, is m plus n over m times n a rational number? Yeah, because the denominator is not 0, and the product and sum of integers is integers, are integers, so they're, the result would be a rational number. So we went through that, and yeah. Yes, and no, 2 over 0 is not a real number. Division by 0 is not allowed. No, because every irrational number is a real number. And 2 over 0 is not a real number. Yeah, 12 over 99, that's the ratio of that. Yeah. But, yeah, so, and the zero product property law, if neither of two real numbers is 0, then their product is also not 0. So, more on generalizing from the generic particular. All right, so most problems are stated in informal language, but solving them requires translating them into more formal terms. Like, every integer is a rational number. Proving properties of rational numbers. Prove that the sum of any two rational numbers is rational. Well, write it out as for all real numbers R and S, and if R and S are rational, then R plus S is rational. Where are you starting from? And where are you going? So, suppose R and S are any particular but arbitrarily chosen real numbers, such that R and S are rational, or more simply, suppose R and S are any rational numbers. What must I show to complete the proof? R plus S is rational. How do you get from the starting point to the conclusion? Or why must R plus S be rational if both R and S are rational? Answer depends depends in an essential way on the definition of rational. Rational numbers are quotients of integers, so to say that R and S are rational means R equals A over B and S equals C over D, where A, B, C, and D are integers and B and D are not equal to 0. Then by substitution you get this here, and then you rewrite the fractions as with a common denominator, and then you do adding fractions with a common denominator, and then this fraction is a ratio of integers, because products of the sums of it and sums of integers are integers. AD plus BC and BD are both integers. BD is not equal to 0 by the zero product property, and thus R plus S is a rational number. So you get theorem 432. Deriving new mathematics from old. Suppose that you already have proved the following properties of even and odd integers. Sum, product, and difference of any two even integers are even. Sum and difference of any two odd integers are even. The product of any two odd integers is odd. The product of any even integer and any odd integer is even. The sum of any odd integer and any even integer is odd. The difference of any odd integer and minus any even integer is odd. The difference of any even integer minus any odd integer is odd. Use the properties listed above to prove that if A is any given integer and B is even integer and B is any odd integer, then A squared plus B squared plus 1 over 2 is an integer. So you go through and do substitution and, property 3, B is odd, and property 1, A squared is even. Then the property 5, A squared plus B squared is odd. Because 1 is also odd, the sum A squared plus B squared plus 1 is even. And then by substitution, there exists an integer k such that A squared plus B squared plus 1 is equal to 2k. Divide by both sides by 2 gives this here, A squared plus B squared plus 1 all over 2 equals k, which is an integer. Therefore, the A squared plus B squared plus 1 over 2 is an integer. The double of the following, the double of a rational number is rational. Well, it's a corollary because the double of a number is just the sum with itself. But since the sum of any two rational numbers is rational, theorem 4.3.2, the sum of a rational number is with itself is rational. Hence, the double of a rational number is rational. Just a simple 3-statement proof. And I believe that will just about wrap it up for the day. So